All right, chemists, today we're going to add a little bit more to our heating and cooling curve. So you would break out your blank heating and cooling curve. You can either add it to the original document, but if you're getting a little too full up on that one, print yourself another document, or I'll have a paper copy in class. So let's remind ourselves that when we're talking about heat, what we're talking about is the flow of energy due to temperature differences, and heat does not travel up. Heat travels from hot to cold. We measure it in joules or calories. There is a conversion factor right there. 4.184 joules is 1 calorie in case we need to convert. Now, we're going to have a couple formulas that we're going to add. One of them is going to be this one. This is going to be the formula that you will use if you are in a part of the graph where the temperature is changing. So the densities of materials change when they're in different states of matter, the different phases. So the specific heat capacity, which is going to be either S or C, you're going to see both of them written in formulas. So you're going to see a formula which is SM delta T, or you're going to see the formula written as and referred to as the MCAT formula. Both of these formulas are the same because specific heat capacity and specific heat capacity are essentially the same thing for our purposes in this level of chemistry. Later on, you'll learn the difference between those two. Okay, so remember, we talked about different states of matter have different specific heat capacities. So you'll see that water is actually the highest specific heat capacity, meaning it takes the most amount of energy to change 1 gram of water by 1 degree Celsius. So if you notice, it's the amount of heat needed to change 1 gram of water by 1 degree Celsius. So that's where those units come from. These are reference numbers, so they will be given to you every single time you're doing one of these problems. So the specific heat capacity is going to be different for each substance. The larger the value, the longer it takes for a substance to heat up, the more energy you have to add to change the temperature. Liquid water has a high specific heat capacity, and things like metals have a low specific heat capacity. That means when you add a small amount of heat to a metal, it will change temperature by a greater amount than, say, water. And we know this because if you had a metal chair sitting outside next to a little kiddie pool full of water, the metal chair is going to be hot, the water is not. So here's our second equation. It says Q equals heat of fusion or vaporization times mass. So this is what you're going to see the formula written as. If you are changing states from solid to liquid, it will be written like this: the heat of fusion or enthalpy of fusion times the mass. If you are changing states from liquid to gas or gas to liquid, it will be the enthalpy of vaporization times the mass. So if you notice, it's the amount of energy to change this phase of the substance, in this case water, the amount of energy you need to add to change liquid water to gaseous water per gram, or the amount of energy you need to remove to change gaseous water to liquid water in joules per gram. The heat of fusion is between solid and liquids. The amount of energy you need to add for each gram of water to change a solid to a liquid, or the amount of energy you need to remove from a liquid to get it to change into solid. Again, these are reference materials, so you don't need to memorize that. So the next thing you want to do is get your heating curve out. Notice that each individual area in the graph, we have 1, 2, 3, 4, 5 sections of the graph. Each one of them gets a different constant. If you are not changing temperature, then you're changing phase. Then you use the formula that does not have the temperature change in it. So on your heating and cooling curve notes, add the formula without the temperature change to the phase change plateaus where the temperature is not changing. Write down the individual reference number for each phase change. Also take a look at the fact that the number to change solid to liquid or liquid to solid is much smaller than the number to change liquid to gas or gas to liquid. That's because the phase of liquid and gas are so much different than each other. The phases solid and liquid resemble each other more closely. They are more similar to each other than liquid to gas. The next thing you want to do is add the other reference to the temperature change. So the specific heat capacity of ice is 2.03 joules per gram degree Celsius. The specific heat capacity of liquid water is 4.184 joules per gram degree Celsius. The specific heat capacity of water vapor or steam is 2.00 joules per gram degree Celsius. These are all in sections where the temperature is changing, so you're going to use the temperature change formula. Add all of this to your notes. The key is when you're using this reference material, Q is going to be in joules, mass, or M, is going to be in grams, and T is going to be in degrees Celsius. You might be given your reference materials in joules per mole degrees Celsius or something like that, or joules per mole, but that's okay because we know how to change grams to moles. We're going to work on the actual calculations at a later date. So for your quiz on Wednesday, the calculations will not be on there, but you will have to be able to attach the correct values to the correct part of the graph.